this small thing that had literally nothing until a complex protocol that basically survived for 15 years. Since when HTTP2 was introduced? 2015? Like 15, somehow 15 years that the protocol wasn't really changed. We just used those basic primitives and enhanced them over time. And by protocol extensions, I also mean those things. So we have HTTPS, which is also was able because of the flexibility of the protocol. We have WebSockets and SSEs, which are not some new protocol, are not like HTTP2. They're just extension over the basic protocol. And we also have new architectural patterns like RPC and REST that now we can communicate over HTTP to produce complex operations, like communicating over microservices, like doing complex computation over a single HTTP call, just because it's convenient, and that's all.
Let's talk very briefly about the HTTP request lifecycle. So when the client can be your browser, can be any client at all. And to initiate a transaction, usually we want to have a domain or a web host. So we're gonna say, hey, I want to communicate with google.com. So we're gonna go to our DNS resolver, which basically gonna be either ISP or some other DNS provider that we configured at our system. After that, we're gonna have an IP, and we're just gonna start TCP handshake, basic TCP socket. After the handshake passed, we just have the simple flow of, hey, that's my payload for the request. I need that endpoint with those headers and maybe extra values, and we're getting a response back. Simple as that.
So just a couple of words about the low-level part, the TCP and the DNS part. So we just start from some URL, which we're going to talk to you about that in a second. And from that URL, you want to get HTML. So first thing that you have to do is understand who you're talking to, which server on the internet. And servers on the internet are addressed by IP addresses. So you need to do this conversion from hostname to IP address, and this is done by DNS. And DNS is completely separate from HTTP. It's like a completely different part. But you have to go through it first thing. The DNS resolver might be local, might be a host file, might be some DNS daemon that you have on your laptop. Some operating systems have like DNS caches, local. Also might be your ISP, might be Google, 8888 for anyone who uses that. And then you start the TCP handshake with, how many round trips is a TCP handshake? 2, 3 round trips. Yeah. So it's actually 2. It's like one going forward and going backwards. This is 1 round trip. And then the second one is the ACK, and usually you send data with the first ACK and with the second ACK. So actually, like the HTTP request usually goes with the ACK, with the packet. It's kind of an optimization. It's not mandated by the protocol. It's an optimization, but this is how it usually works. And then you get a response. So let's say that you have a server that is 100 milliseconds away. Okay, how long before you get a response? And suppose like processing takes 0 time. How long before you get a response?
100.
Sorry?
100.
No. How many round trips? If each round trip is 100 milliseconds, 200, exactly. Minimum. Okay? It's cool. So that's that. So this is what TLS looks like. So we're usually using HTTPS on the internet today. At least we hope that you do. If not, that's kind of tough. Anyone knows what the difference between HTTPS and HTTP is? Sorry? TLS handshake. Yes, TLS. So TLS is an encryption layer. Okay, it's bolted on top of TCP, just below HTTP. So you have TCP, and then you have TLS, and then you have HTTP. Okay, and TLS has a lot of benefits, provides a lot of value. It encrypts our traffic in transport. The problem is, of course, you have the TLS handshake, and also you need some kind of state for TLS. It's not part of the HTTP protocol; it's part of the TLS protocol. But the servers do keep what is called as an SSL token on their side, and the client keeps it on their side. So let's go through the connection initialization. So we have DNS resolver again. We have DNS request, which resolves to an IP address. Then using that IP address, we open a connection to the server, and we do the SYN ACK, like SYN plus ACK, and then another ACK. And with that ACK, we already initiate TLS handshake. So the data transfer there is the client hello, okay, the first part of the TLS handshake, and then we get the server hello, and then we exchange keys, and then at the end of it, when we're done exchanging keys, then we can send that HTTP request, okay? Now, you would notice that this added 2 round trips, okay? 2 round trips. So let's go through it again, using our previous example. 100 millisecond latency, round trip latency to the remote server. How long before we get the first answer? How many?
400?
400? Yes, it's usually between 400 and 500, depending on the exact state of the TLS handshake, which is horrible. Like, think of this. 100 millisecond round trip is from here to Europe, to London maybe. Okay, if you're connecting to a server in London, you're going to have to wait half a second before you get anything. Like, this doesn't even include the time that the server takes to process the request. So that's pretty horrible. Okay, so what? What can we do? Like, obviously, this is not how the internet works, right? Like, otherwise, most of the devices would be unusable. This would be like a horrible experience. This is sometimes the experience that you get when people don't know how to deal with this. So, how are people dealing with this? So, let's go through this again. Okay, we have 1 round trip for DNS result, which, like, we didn't even include this in the computation. By the way, people don't know this, but which protocol does DNS use? Sorry, UDP. And what's one of the characteristics of UDP?
Unreliable?
Unreliable, meaning it's lossy. So what happens if I send a request to a server and it doesn't answer? I try another one. How long before I try another one? Ooh, interesting question, right? So that's the problem. The problem is that, first of all, in most operating systems, DNS is blocking, okay? Meaning that if there is some retry, we're going to have to wait. Just sit there like dumbasses and wait till we get a response that may or may not be coming back, which is kind of annoying. So DNS is like a horrible performance problem, but it's usually cached after the first time, so somewhat mitigated to some degree. But if anyone using Node.js, yeah, look up DNS problems with Node.js. Really, a lot of fun. Yeah. So that's 1 round trip that we have to go through. Usually fairly short because you get DNS from ISP or cache. But if not, well, that's tough luck. Then you get the TCP handshake. Then you get 2 round trips for the TLS handshake, and then another one for HTTP. So this is why the mouse is 500 sometimes. So what can we do? First of all, DNS caching that we talked about. Second is TCP connection reuse. Okay, remember HTTP 1.1 added connection reuse, meaning that we can use the same TCP connection and send more HTTP requests on the same connection, meaning that we don't have to go through the whole connection initialization phase, not with TLS or TCP. We just use the same connection. So assuming that we already talked to that server once, second time it's just going to be 100 millisecond back and forth. Okay. Then we have HTTP pipelining, which we'll talk about in a bit. Basically, it allows you to send multiple requests in a batch, meaning concurrently, and get the responses also in a batch. Really nice optimization. We'll talk about that in a second. TLS also has a very nice feature, meaning if I spoke to a server and I already exchanged the keys with that server, I can cache the token, the session token, for several hours, okay, depending on the exact configuration of the server. And if I talk to that server again in the next, let's say, 6 hours or so, I can just say, oh, look, I've got the keys already, so we don't need to exchange keys again. That saves 1 round trip. So that's amazing. Shaves off like 100 milliseconds. Not too bad, not too shabby. And then Google introduced TLS 3.0, okay, new standard, yes.
Can I ask about the TLS session reuse?
Yes.
What you said?
Yes.
It's like it's using a cookie and give you like a token?
It's not a cookie. It's SSL token, it's called. Okay. It's somewhat like a cookie. It's state that the client and the server have to save. Okay. It's the identification of the peer. Okay. So if I'm a server and you're the client, then I know that for you, okay, I have this key that we already agreed on, and I can save it somewhere, okay, in memory or on disk or wherever I want. And when you talk to me again, I'm like, oh, okay, I know you. I have the key already. You have the key already. Let's talk. Okay, so that saves the whole initialization process, which is really good. TLS 3.0 actually with quick, which HTTP 3, you can actually have, it's only one round trip to initiate the session, and if we already talk to each other, it's like 0 round trips to initiate the session, which is amazing. A lot of performance benefits, not widely available yet, but it will be in coming years, which is amazing, and CDN. So how does CDN help here?
Gets the content closer to you.
Yes, but we're not talking about caching here. We're talking about just the TCP TLS part.
Making the round trip shorter.
Exactly, making the round trip shorter. So that's the first thing that it does. So the CDN, usually they have a box in, let's say, your ISP. And the latency to the ISP might be like 10 milliseconds, okay? So doing even 5 round trips, okay, to the CDN, to the ISP, would be like 5 times 10 milliseconds. So that's like 50 milliseconds to initiate the connection. And then the CDN is usually already connected, or they already have a session, a connection open to the backend. Okay, so even if they don't have the content that you asked for cached, they only need 1 round trip to get it, so that's 100 milliseconds. So we're down to 150 milliseconds from about 500, which is amazing. Okay, and usually the CDNs also have further optimizations, like they might have a better internet connection to the backend because they may be paying more for upstream, or maybe they have different routers or whatever. Usually they have their own private networks, so it's usually not even 100 milliseconds, might be like more like 50 or 60 or something like that. So it's a really big optimization, and this is why you want to be behind the CDN even if you're not doing any caching, just for the SSL termination. Okay, so very beneficial. That's also kind of a problem, because this means that CDNs, and Michael is going to talk about that in a bit, about virtual hosting, they need to serve a lot of websites. So they need a way to differentiate between websites. They need to know who you want to talk to. And how do you know who you want to talk to, okay? And you need to tell me this, but you want to tell me this in an encrypted session. So how do you tell me which certificate to load before, we have some kind of encryption? So that's kind of we're going to leave that as an open question, but if you're interested, look up SNI online. Really cool. SNI. Yeah. Look it up.
Now back to the fun part. So HTTP request usually looks like that, and what we're trying to see here is how the actual payload looks like. So what's the autonomy of the request? The first line always indicates the meta type. So in this example, we're trying to send post request to some endpoint using HTTP 1.1. What you can see here that the protocol specifies that the request line would contain the meta type, the actual requested resource or URI, and also after HTTP 0.9 or 1.0, they also added the mandatory field of adding the HTTP protocol version. The reason why we're adding it here is for a very simple reason. You know that most of the web servers are backward compatible, because HTTP is usually backward compatible. You can downgrade or upgrade sessions. So even if you have an HTTP 1.1 web server supported, you still may send 1.0 request. And the way to differ between those requests is by this request line. Then we have the headers, the metadata, the thing that makes HTTP fun. And here we have all the content, all the metadata relevant for our request. So if you look in this example, we're saying that we're sending a content type of application JSON. The content left is totally incorrect. It's not free, it's more than that. It's at least 12. If I manage to count it correctly. And we're trying to send a request from user agent HTTP pile. Those 3 blocks, or those separators, is how HTTP request looks like. Note that we have a new line between the header and the body part. It's not by mistake. It's the way we differ between headers and the body itself. Also, it's important to say body is not always included. So in this example, we're sending post request, and post request requires us to send a body. But if we send a get request or delete request, it wouldn't matter. We just see the request line and we'd see the headers.
Just kind of a riddle. We kind of cheated here. Also, the content length is not exactly the cheating part, but so it's also the cheating part, but there's also another cheat there. So who can identify where we cheated? Sorry, not user agent? No?
But something else.
Something else. You can send whatever user agent you want, by the way.
The hint is
Charles said, no, close.
yes.
Jay-Z, very nice. How do you know that we cheated?
זה לא זיפ, זה...
נכון, it's not binary.
Just because you can read it.
You
That's
can
all.
read it. If it's gzip, how can you read it? So very good. Nice. You get 2 points.
And we also said connection keep alive and it's
So not
slides.
worth anything.
So that's the host header I mentioned before. The host header is the one that allows to distinguish between different web servers. So Avishai briefly mentioned virtual hosting, and we're going to talk about it a bit more on our slides. But just in a high level, the host header is something that allows to do complex stuff like having one single web server that handles different sites. And if we look in like 90s and beginning of 2000s, we had lots of Apache installation or HTTPD that we had virtual hosting files. So how we would distinguish between different websites? Just because HTTP 1.1 required this field to be mandatory, every web server can do special routing based on that host header. So if you're hosting 5 sites on a single server, we know how to route between them only by that. The content negotiation part. So here we can see the client says, hi, I'm willing to accept application JSON as the response. And we also lied again here saying that we also want to accept encoding for gzip, while it's plain text. What's interesting to see here that besides the gzip itself, the response here is a JSON. We also could receive here other error that we're going to see in the further slides. And that's how we're telling the server what data we want from the server. I think if there wasn't such ability, we would probably be lacking so much power of the HTTP, and just because of those headers. And the entity headers are used to specify the payload types. So besides the fact that we said we're willing to accept JSON as the response, we're saying we are transmitting you now a JSON payload of a content length of fix. Do you know why we even send content length? Like, what's the problem of reading the payload and not caring about the length?
Checksumming? Nope. Why would we need, one second, why would we need checksumming?
For 2 purposes. 1, you want to know that you got everything.
Okay.
And 2, you want to make sure that you didn't get something additional.
Okay, so that's a good point. But so going with this state of mind, why would you need content length?
Make sure you got all the data.
Okay, that's yes, more or less. But why is it so important to make sure that you got all the data?
So you want to accept another packet as a follow-up for the missing data?
Yes, that's more. We're getting there. Yes. So suppose
you're reading the content into a buffer, and if the buffer is you don't have enough size, then you'll just get a null pointer accepted.
almost. The basic question is this: if you're using TCP, TCP gives you an abstraction of an infinite stream of data. Okay, and if you have an infinite stream of data, when do you stop reading from it? Right? Like, when does the body end? Maybe it's like 10 megabytes, maybe 100 megabytes, maybe it's a stream that never ends, right? So how much do you read from the stream? So you need to know, which is why we have content length.
I wanted to keep it as an open question because we're going to handle the same issue in a workshop on the hands-on part. And let's look a bit of how the response actually looks like. So the server is saying back, hey, I'm still talking in the same protocol, and I'm giving you now a status code. The status code identifies how the response behaves. So in this case, or in this example, we can see that the request went fine, and we got 200 OK. Does anyone know why we're saying OK? Why not just saying HTTP 11200? Why we need extra string, extra bytes on the network, and just simple? What?
There are different types of okay.
What would happen if it sent 200 not okay?
Depends on who accepting the response.
But the response code here is 200, but the string nearby it is not okay.
Maybe in something like logs, you will see like 200 and then like error or something.
So we're gonna also see it in the workshop of the Python, but I'll give you a spoiler, maybe it doesn't have any meaning, or maybe it does. So let's look at the headers again. We're having the status line, the same like in the request. We have the request line, here we have the status line, then we have the headers. And we again have the same pattern of new line and then body. That's how we separate between the metadata of the request, which is the header and the status line, to the actual body. And we can see here just the basic document HTML and many headers that specify like caching and again gzip. And those the caching headers. You can see in this example the response gonna be cached by the browser specifying by the time we send. And the tag specifies.
Usually it's a hash. It's an MD5 hash. I kind of cheated here, but you get the point.
And that's how we use the protocol to leverage cache on the browser. We can say to the client, hey, this content probably not going to change for at least X amount of time. You don't actually have to refetch it. You just can store it in your backend. And browsers do care about those headers. Usually your HTTP clients doesn't, because most of our HTTP clients are just stateless apps. But we can't and should leverage those things.
Okay, so 1 second. Before we talk about the URLs, I want to make a brief stop so we can go into Strigo and do some demos and then start the first exercise. So please open your browsers and go to this address, okay? And at some point it's going to ask you for a token, which is written just below the URL. So we're going to wait a few minutes for you to do that. Okay. Okay, cool. So I'm gonna use Netcat. Everyone knows what Netcat is, right? Cool. So Netcat is like a utility that allows me to send raw data to a socket. Okay, so I'm going to try and open a connection to www.google.com. Okay, on port 80, which is like the standard port for HTTP. Okay.
.con is nice.
What's right?
.con is nice, but it should be .com.
Yeah,
.com. Yeah. Yes. I would argue that Google is some kind of a con job, but
maybe they have the domain.
Yeah. And now I'm going to craft my own HTTP request. Okay. So you're going to help me. What is the first line of an HTTP request? Get / right? HTTP. כן, אני יכול להגיד את המסך. Okay, should represent code. So HTTP. Okay, so sorry. 1.1. Okay, and I need to give it some headers, right? So headers, but let's give it a header host. Header www.google.com. Okay, and maybe user agent. Foobar, because it's totally Foobar what I'm doing here. Okay, and I want the content type of, we want text HTML. Let's say we don't actually care about the child set, but let's give it anyway. UDF-8. Okay, so those are the basic headers that I need to send. Like I don't actually need to go through it more because technically speaking, GET doesn't need to have any content. So I don't need content length. I'm going to send it anyway. It's going to be 0. Cool. And boom. 2 enters and I got a response. Okay, so going back up, let's look at the response that I got. You might want to do this yourselves as well on your own personal instance to see what's going on. So this is the payload, basically. As you can see, lots of HTML and JavaScript and then other stuff that we don't want and care about. Okay, so, but here we have the headers, response headers. So let's look at what happened. I clicked 2 enters, like I sent 2 new lines. This tells the server that the request is terminated. Okay, so it knows that, okay, that's it. it can begin processing it. Okay, if you remember, because there's content length 0, this is how the server knows it doesn't need to expect more data. Okay, it can just start processing and send a response, and then it responded with this lovely response, which is okay. The protocol level is 1.1 as negotiated, 200 okay. The date, okay, when this request was crafted, expires -1, which means don't cache ever. Okay, cache control also says it's private, meaning don't cache it, and max age of 0, which means don't cache it. You will notice that they tell you don't cache it several times. They really mean it. Okay, so content type text HTML as we requested, but you would notice something a little different. We requested charset UTF-8. They gave us something else. Yes, they gave us ISO 88591. Okay, so content. Sorry. Sorry, you wrote the wrong header. I wrote content type instead of accept. You are correct. Thank you. So this is why they gave me the default charset. Thanks. The server header. Okay, this means this is not mandatory, but most servers will have this. It tells you which server is serving you the content. Usually it might be Nginx or Apache or whatever. GWS is Google's proprietary server. Okay, it's a nice way to identify the servers on the internet, like which program they're running. However, it's also very easy to change. So you might see whatever string they want to put there. For example, when I worked at Wix, we use Nginx, but they compiled it such that the server header is Pepiaka. So yeah, he's laughing. Russians. So you get the point. XSS protection, like more metadata, set cookie. This is how cookies are being set. Okay, so we didn't talk about cookies at all. Cookies is not, strictly speaking, part of the HTTP protocol. It's like, it is actually part of the HTTP protocol, but we're not talking about that. It's like kind of an extension, mostly for browsers, okay, which is why we're not talking about that. But it's also set in the headers. There's a special header called set cookie, and the request also has a header called cookie, which can be can appear multiple times. We didn't say that before, but headers can appear multiple times. Okay, it's not a single header. You might have several lines with the same header key. Okay, so if anyone is using like hash maps to store headers, you're doing it wrong. Seriously, I've seen this many times. No, just no. Okay, as you can see, several cookies are being set. Okay, and then you get accept ranges and stuff like that, and then you get one line, new line, which terminates the header part, and you get a body. Okay, so I'm going to ask you a question. We didn't see content length here, right? Why not?
Yes.
Sorry?
No, it's the response.
In the response, there's no content length.
It's the entire TCP session.
No. So how does the client know when to stop reading from the stream? So you see this, what, sorry? So Michael mentioned this earlier, okay? Chunked response or chunked body. Okay, so you see the transfer encoding chunk here. Okay, so this is a slightly different protocol for sending body. Basically, we send data as a stream, chunked stream, and every chunk is terminated by, again, new line. And you can send several chunks. Okay, we're going to talk about that later in the workshop when we get to streaming and something called server-side events. But this is like the basic idea. This is how you can send presumably infinite amount of data or a lot of data without needing to know in advance how big it is. Okay, so you can actually send streams over HTTP. Fun fact, all the video that you see online on the internet today is using HTTP. Okay, Netflix, YouTube, whatever. A long time ago, we used to have specialized protocols for video like RTSP and stuff like that. RTMP, no one uses that anymore. Now everything is on top of HTTP. And the way that works is because we actually have streaming in HTTP nowadays. So this is what transfer encoding chunked is for. So really cool. And this is like the body, we don't care about that. Yeah. So this string here, thank you. This is basically the chunk header. Okay, the full string here. which tells the client how big this chunk is. So the chunk protocol basically is, I'm going to tell you how much, it's like content length more or less, but for chunks. I'm going to tell you how much data I'm going to send this chunk, and you read off the stream that size of chunk, and then we're going to terminate that chunk, and then we're going to send another chunk in the same format, and so on, so on, so on. Okay, that's basically the idea. Thank you. Very good. So, has anyone tried it with Netcat on their laptop? No? Anyone? No? Yes? Cool. I highly recommend that you try it, okay? And you can actually implement a Netcat based server as well, not only a client. It's not very, very hard. There's actually a framework, look it up on GitHub. It's called Bash on Balls, okay? It's like, everyone knows Ruby on Rails, so there's Bash on Balls. It's something horrible, really, really horrible. Like your eyes will bleed if you look at it, but it's fun. And it's basically a web server with Netcat and stuff like that in Bash, because why not? Yes. Okay, so the last chunk, okay, how do we know that it's the last chunk? One second, so you see the 0 here on the bottom, okay? This basically tells the client, this is the last chunk. I'm saying the last chunk is 0 bytes. Okay, so you know that's it. That's how we know. Cool. Okay. So the way the workshop is going to work is you all have HTTP folder cloned on the thing. You don't have it cloned? Shit, it didn't work. So clone it. Just clone it. Okay. HTTP GitHub Avishai Shalom / HTTP, and now that it's cloned, you can just go in there and we can start the workshop. And I'm going to show you a little bit how Strigo works, okay? And then you can implement the first exercise yourself. So the way that it works is, first you have terminals here. You can open more windows if you want, okay? Very easy. You have the plus button. And then you've got here the whiteboard, the slides, and stuff like that. And most importantly, you have an editor, okay, which allows you to edit. I personally prefer to use Vim, but you can use like the built-in editor or whatever it is that you prefer, okay. And inside of HTTP, there's a levels directory, okay. You go into the levels directory. Inside there's level 1. It's like a game. You go into level 1, and there are 2 files there: README and server py, okay. The README, it's easier to read it off of GitHub, so open the GitHub repository and just it's rendered as Markdown there, so it's much easier. So I'm going to do that just to show you what's going on. So levels, level 1, amazing. So what are we doing in this exercise? It's a warm-up exercise, just so we know that you're all comfortable in Strigo and using Linux and Python. And just basically have to edit the server py and implement the response to a request. Okay, so the way that you know that the exercise worked is if you successfully use CURL or whatever HTTP client to submit a request and get a response, like a valid 200 response from the server. Okay, so 1 second. Going back to Strigo, I'm going to do vi server py. Okay, so this is what it looks like, and you see where the to-do is. Okay, so throughout the workshop, we're going to edit the Python files and the places where you have to do the edits, where you need to add your own code to solve the exercise, are clearly marked in to-do, so just look for to-do, and you know what to do. Okay, so now that you know what to do, go and do it. Okay, you've noticed in the README that there are links to the necessary documentation, so yeah, feel free. Yalla.
And don't try to do all the levels, because we still have content on our slides, and if any one of you managed to pass level 4 in the next 20 minutes, it's going to be amazing, but please try to avoid passing it.
Yeah, please don't ruin our workshop by being too good. Thank you.
Yes, be slow, please.
Another thing, we're going to be walking between you people, so if you need help, just do this, or say, come help me, or scream, I don't know, whatever. The link to clone the workshop, okay, on the bottom. if you want to access your machine from the browser, sorry for interrupting again, okay? So there's machine info here. Okay, and you can see the address of your machine here. Just copy this into a browser, okay, and you can use it in the browser. Okay, all the ports are open. Cool.
Raise your hands who finished level 1. Who finished level 2?
No, don't do level 2 yet.
Right.
No.
Who didn't even start?
Okay,
Great,
cool.
that's the most important. Any one of you managed to get to level 4? If so, please stop being so fast and stop.
So we're not going to do all the levels just yet. We're going to take it one at a time. Okay? So
To do the whole thing now, or?
don't do level 2 until we tell you. Don't do anything that we don't tell you to do in general, like in life. Okay? Cool. Breathing is fine,
On in specific intervals.
but on specific intervals. Thank you. Cool. Okay, so I'm going to show you like the solution very fast. Okay. I'm going to walk you through the solution, what's going on. Okay, so see the levels, see the HTTP levels, level 1, amazing. Okay, so P1, okay.
Everyone
So,
see the screen?
everyone sees this? See what I'm doing? Okay, cool. So the pass statement in Python is just a no-op. It doesn't do anything. It's just there to fill the space because we need something in the block for the code to be valid. We don't need it, so I'm going to change it. I'm going to remove it. And I'm going to do this. So serve send response. Okay. So this is like a method that sends the response line, the first line of the request. The response, sorry. I'm going to send OK. And then I'm going to send some headers. So send header. So in this case, I'm going to send server header. It's a demo server, so I'm going to write demo here. Okay. And then I'm going to do end headers. Now this part, most of you didn't do, and it's actually very, very important. What does it do? End headers. Anyone want to take a wild guess what does it do?
No more space.
Sorry?
It's a new line.
Yes, it sends the new line, but more importantly, it flushes the buffer out into the TCP stream. Okay, because when you're using TCP, okay, you can write to a stream, but it actually writes to a buffer, and you don't necessarily flush it until the buffer fills. So you don't know exactly when the client's going to get it. You don't know that you actually sent it. So end headers is doing two things. It's inserting the separator, the new line between the headers and the body, and basically tells the client, okay, I'm done. Okay. And second thing that it's doing, it's flushing the TCP buffers and making sure that the data is being sent to the client. Okay. So that's what it's doing.
You don't actually need it because you have it in the end.
Yes, you don't actually need it because you have it in the end, which is why I put it, but I'm just putting it there because we're going to use it later, so just so you see what I'm doing, okay? So, wait 1 second, sorry, I'm going to delete those two lines now. So D to D, cool. And this is basically just a warm-up exercise. It's pretty easy, pretty cool, cool. So anyone tried setting something that's not okay as the response string? Yes, what does it do?
Nothing.
Just
Send it.
Except
Yes.
you see it.
Except that you see it.
It's for you.
Yes, it's for humans. The machines don't care. The machines only care about numbers. I am not a number. I am a human being. Woo! Yes. Whatever. Okay, so congratulations on completing the first exercise. So there are some subtle differences. Okay. So first of all, the URI is an identifier. It's assumed to be canonical. Usually in REST, for example, it means like this is the identity of an object, for example. And there are some other small differences like allowed characters. There are slightly more characters allowed in URI than in URL. Like really, really annoying small semantic differences. But for most people, it's mostly the same, kind of interchangeable, unless you use like really like REST clients, which might be sometimes kind of anal about it. But yeah. So we're talking about URL specifically here, but most of what we say is also applies to your URI. Also, there's something called URN, okay, like name, universal resource name. Again, not going to go into that, but Cool. So the nice thing about the anatomy of a URL, it basically allows you to see the structure of the internet in one line. Seriously. So let me explain what I mean. So if you look at the URL, okay, it's divided into several parts. First part is the protocol, HTTP or HTTPS, which means what language do I use to talk to the server? Is it encrypted? Is it not encrypted? Okay, which protocol should I use? Except HTTP and HTTPS, anyone knows other protocols that can be used in URL? Git, more, another stage. FTP, very good, FTP. In the old days, there used to be like Finger and like more other obscure protocols that no one uses anymore. But in general, you can in the URL use, and browsers do support it, stuff like FTP, okay? So FYI. Then you get the host name, okay? So the host name can be an IP address or a host, like a DNS name. And this part is actually not handled by HTTP. It's handled by the TCP layer and the DNS stack, and the DNS layer, okay? So this part is handled by the operating system, or if the client has its own stack, TCP stack, it's by the client. And then you get the port. So the host part is who do I talk to? Who on the internet do I talk to? How do I get there using IP? What machine on the internet? I mean, getting to that kind of things. And the TCP, like the port part, what is a port? What is a port? You're all using ports. What is a port? But what is a port? What is a socket? Come on, what is a port? What is the port number? What is the number of?
A location in the operating system for communicating.
Correct. You might have several channels, several communication channels in the operating systems. Okay, they might belong to different processes on a single server. Server can run multiple processes. And when the operating system receives a packet, it needs to know which process and which specific channel this packet belongs to. Okay, and this is a port. The port is basically a number. It's nothing more than that. And you can use basically any number you want, but certain numbers have been standardized. So, for example, 80 is the default port for HTTP servers. We chose a different port for our server in the lab, 8080. Basically, you can use any port you want. You just tell the browser, but if you don't tell it anything, it's going to use 80 by default. Okay. This also has one very interesting consequence. It means that anyone that's using firewalls, air quotes intended, to block ports as a defense, okay, is basically fooling himself because a port is just a number. That's it. Like you just change a port and that's it. So I don't know why people do it, but they do. So moving on, we have the path. After the port, we have the path. Okay, and what is the path? The path is basically on a web server. First of all, you might have multiple resources on a single server, maybe different pages, maybe different even programs. For example, if you remember the old days when we used to put like multiple WordPress instances on a single server, so they were discriminated by a different path or different path prefix. Okay, so it basically tells you which page or resource on that program or server you want to get. And then you get the query string. The query string is basically parameters for the application. Okay, we're going to talk a little bit about that when we get to caching. But strictly speaking, it's like the path is like which program on the server I want to activate, and the query string would be which arguments I want to give this program. Okay, that's like more or less the semantics of it. And this is on a GET request. Like you can put query string on any type of request that you want, but it's usually, it's more of a, it's not exactly a protocol, it's more of a agreement that people have, that mostly GET requests use query string, and if you have parameters that you want to send in the post, send it in the body. It's not mandatory, but this is how most things work. Sometimes a lot of programs can read the parameters both from the body and from the query string. Yeah, it has ups and downs. I have encountered some security people who are like, oh, don't put stuff in query string, it's not secure. Yes, of course, it's bullshit because anyone can just open the body and look what's in the body as well. And if it's encrypted, then also this line is encrypted, so yeah.
Could To use the query, you have benefits for it if you want to save the state of some of a page. I mean, if you
in a bookmark, yeah. So that's very true. Because you save URLs in a bookmark, if you put the state in query string, you can actually save the state as part of the bookmark. This is why Kibana, for example, they put the entire query that you do for Elasticsearch on the URL. It does have some downsides. For example, it has limited length. If you need like a lot of data, probably URL is not a good idea. Okay, so then the last part is called the anchor. After the hash sign, the pound sign. Okay, so this is called an anchor, and this is handled by the browser. It's not even sent to the server. Okay, so little known fact, you can give parameters to a web page which go directly to JavaScript. Okay, to the client side part of the program, and they're never transmitted to the server. They're not like the server don't even know they exist, but it's still part of the URL. It's basically the information that is sent to the client side code if you have any. Okay, so it's very convenient if you have like a service SPA, single page application, client side program. You can save in the URL parameters for it and stuff like that, and it will receive it through the browser. So very nice. So here you can actually see the anatomy of the internet. You have on the right side, you have the browser, the client, okay, which receives parameters. It talks to an app, which is on a server, okay, on an operating system, on a server, and which you get to through TCP on the internet. Okay, that's how it works. Yes.
Just a nitpick, you wrote HTTPS on port 8.
Yes.
Makes sense.
Yes, I wrote it on purpose. You know why? Because ports are bullshit. Remember, you can talk HTTPS on port 80. I know, it's confusing. It's not default. The default port for HTTPS is 443. Okay, but you can talk HTTPS on port 80. You can talk HTTPS on any port you want. Okay, so this is very important to emphasize. Yeah. A lot of modern day software uses HTTPS on like various ports. For example, if you're using Vault or Console or stuff like that, they all talk HTTPS or HTTP, and they use whatever port they want. I don't even remember what's the default port. For Elasticsearch, for example, it's 9200, like 9200s, which is the default port for Elasticsearch, and it's still HTTP. Okay, just on a different port. So. Not to emphasize the point too much.
Fun fact about the port. Why it's 80? Does anyone knows? Why the port is 80? Why 80? Why this number?
Why not?
Why not is the answer. I'm just kidding. But a fun fact, does anyone knows HTTP wasn't the only protocol that served documents over the internet?
No way.
No way, amazing. There was another protocol called Gopher. Which nobody, maybe in the universities or 90s, maybe the older guys maybe used, but it's quite dead, and they had 70 as the port for GopherCon, and for Gopher, and my personal opinion that the reason it's 80 because 8 is greater than 7 to show dominance, but besides that I don't have a clear answer. So let's talk about HTTP meta types. Every request we send in over HTTP needs and has to include a meta type. Meta type is a way to distinguish between different transactions and different operations over HTTP request. So the first and the most simple one that everybody knows is GET. GET is basically, hey, here's a URL. Give me the document, please. Okay, fine. So in this example, just index HTML, and we're going to get the content of the document back. Then we have post. So post is a meta type that allows us to send payload to the server. For example, we want to update our blog post content because we have amazing blog and we have lots of content and we want to keep it updated. We can use post to send stuff like JSONs, like metadata, like data, like basically any byte that can go over the internet. Yes, questions?
Can you put a payload with a GET request? Put a body with a GET request?
Technically, everything is possible. Sure, you can do that, and
but it's not the standard.
It's not strictly prohibited. It's advised not to send a body with a GET. Okay, so the RFC says that you're not supposed to. but it doesn't prohibit it, which means that most of the servers will probably not read it, but it doesn't violate the standard.
That's correct. Let's continue. So then we have the head request, and head request is an easy way to get a metadata on the request. So let's say we want to check if Google responds with a certain header. Instead of sending get request, which gonna return the whole document, we may send an head request that's just gonna send back the headers from the server. The reason I say may because not all the web servers are supporting it or enabling it by default for several reasons I'm gonna mention a bit later. And then we have another few nice types, put and delete. So put semantically similar to post. The way the reason put exists is to differ between operations that are mutating data. For example, we have an existing document and we want to update its data. So for example, for those who are writing REST APIs, it's like the classical case, while put is creating documents. If you actually gonna go to the RFC or to older data around put, they thought maybe it's might be alternative for FTP, for example, because it's plainly uploading files. And you may use it to create, you may use it to update. Again, as the protocol is not that forbidden, I could use post for every operations I want and just distinguish them by URL, right? I could add /create and /upload to distinguish between operations. But I also can distinguish between operations by using the method types, which the protocol gives us for free and give us easy way to distinguish between those. And lastly, delete. Delete is also semantically similar to get in terms of we don't have a payload. We just sent a delete request like a get request that usually it's deleting document.
So are those the only methods? No.
Options.
Options? More? Sorry? Batch? More? Connect. Nice one. Yes, more? Trace? Anyone heard of trace?
Purge.
No, not purge? Yes. Okay. Purge I don't know.
We need a type checker here. Anyone?
Yeah, so I don't know purge, nice. Is it standard? I don't think it's standard.
It's not standard.
Okay.
It's
Okay.
used by Varnish and other reverse proxy servers.
Nice. So trace is standard. There's also something called props from WebDAV, which is like slightly different standard. But on HTTP you have trace, you have connect for proxies, and you have there's options. Okay. So, and the ones that the purge thing that I didn't know about. Yes. Cool.
So those the extra two. Options is may remind head in this case, but options try to see what the available options we have in the web server. So any one of you had a chance to send cross-browser request every day. So we have the concept of cores that try to allow and disallow different domains to access each other. And to allow cores, actually every cores transaction initiates with the options request. The option request asks the server whether I even allowed to send you the actual request or not. So internally, if you're gonna open DevTools and you're gonna see the network, every course operation, and when I say course, I mean, for example, you have a JavaScript that sends, you have a domain called google.com and you want to send a request to bing.com because you want to fetch search results from other search engines for reasons. You need to send two request options to see if you even allowed, and then you can send the actual get or post request. And trace. Trace is a really simple, nice thing that reflects the payload we send to the server. So how do you know that what you send to the server is actually what received to the server? Someone asked that, and they added trace to the protocol, and trace just echoes or reflects back what we sent. I just want to emphasize that, like I think 99, almost every production web server does not allow that, because think that you'd just trying to, or sending malicious requests, trying to get cookies from other people, or just trying to get messed with servers like Facebook guys over here. So you don't want to do that, and usually in production you disable it, but it's a nice utility that most of the servers do support out of the box if you open them with a bug. Let's talk a bit about response code. So we have like those 5 genres of response code. 1x6, every response code that starts with 1 is informational. It just gives us information about the request.
Yeah, so the most common use case for the 100 types is for negotiation. It's like 100 continue. Okay, so I issue a request, like an initial request, and then I get like 100 continue, and then a second request, which is like the actual request. This is usually used by, when I'm talking to proxies or caching servers and stuff like that. You're not likely to see it on your day-to-day routine, so we're not going to talk too much about that. Then we have the 200 success, which everyone knows. So someone asked previously about 200. Are there any other numbers that you know? 201, yes. Created, cool. 204, what is 202? 202, yes, okay, cool. So you know about that, we're going to talk about that in a bit. 3 X's, okay, redirect. Everyone knows and loves redirects, right? The 400 branch is basically, yes, there's an error, but it's not my fault, it's not a server fault, it's the client fault, okay? The client asked something in the wrong way, or we just don't understand the client, or we just hate the client, or whatever, so it's like, shut up, I don't understand what you want to do, talk to me in a way that makes sense, and I know what to do, okay? 500 is an error, but on the server side, so it's basically my fault. It's okay, internal server error, like I crashed, or maybe the backend is unavailable, or something like that. So basically, this allows the browsers or the clients and servers to understand, first of all, should I retry this request? Is there a point in retrying the request? And whether it's my problem and I should debug my code, or maybe it's a problem on the server and like there's no point to debug my code because obviously what I'm doing is fine. Okay, so that's like the basic distinction.
Yeah. Who knows what's 301? Raise your hands. Who knows what's 308, 307? Nobody. And you can see these people's face looking, what the fuck is that? So we have redirects, right? But not all of us knows that we have different types of redirects. For example, for 301 and 302. The difference that we know is that one is permanent, technically permanent, saying to the client, this redirect will always happen. So you may cache it, you may do the redirect always without sending another request. Then you have 302 saying, hey, temporarily, I need to redirect you to other URL. Means that if we temporarily want to redirect other people to HTTPS or to other endpoint for any reasons, we might do that, and any given time, the browser or the client still needs to send the original request to know whether it should be redirected or not. And then the HTTP guys, the RFC tries to fix one issue with those two status codes, is the meta type. If we're gonna send a post request to an endpoint, and that endpoint gonna say, hey, do a redirect 301, does the post method preserved? Anyone knows? The answer is the protocol that care about it. You may or may not. And 307 and 308 added.
What do you mean by preserved?
You want to answer
Yes. Okay. So let's say that I have a form on a web page, okay, and I click submit. So usually submit sends the data as post, okay, and you get to redirect maybe, because maybe I don't know there's a new version of that software, now it's redirecting elsewhere. So what a browser would normally do in this case with the old codes is it would issue another request to the new address, but instead of using post for the new address, it would use get, which is invalid for this form. So this will break the form, will break your site, and it doesn't work. Okay, so this was a problem because it wasn't clear on those redirects whether or not you should use the same method or not, and most browsers, what they actually did was they used get on redirect, which is kind of a problem.
So those two new status codes, they're like 15 years old. They've added HTTP 1.1 and they try to fix those issues, but most of us don't even aware of that because we're so used to C3, 301, and 302 on the web. When we have two other status codes that are fine-tuned to most of the needs, like preserving the method type. And one really important thing to say, redirect loops may and can happen. What would happen if you're going to send a 302 request to the same endpoint? You're just going to have a redirect loop. And fun thing, you're going to implement the same redirect loop in a workshop just after another few slides. And you're going to see how your browser behaving in redirect loops. Spoiler, not very good.
Before that, small question. Anyone aware of 303? 303 redirect? Anyone? Going once, going twice? No? Look it up. Okay, so it's basically the same idea. It was added with 308 and 307. It's just does not preserve the method on purpose. Okay, but now it's like semantically clear. And there's also 304. I'm sure a lot of you have encountered 304. Anyone knows what it is? Not modified, very good. So it basically tells you there's something called like a conditional method, conditional request, where you can ask something in case that there's a newer version, and 304 semantically means local redirect. Like you have it, so redirect to yourself and take the version that you have. That's like basically the semantics of it.
Let's talk about client errors, the 4xx. So one of the things that's important to emphasize here, there's different status codes to distinguish between different error codes, but they also have different semantics. So let's talk about 409 and 408. We have different semantics of error codes that part of them are retriable and some of them are not. So for the very simple example, 404, does anyone knows what that stands for?
Found.
What that really stands for?
The result you asked for is not there. Like,
does it always not available or temporarily not available? Maybe for me, but is it temporarily or always? If I'm gonna go to /index.php,
permission errors and stuff, could be a lot of things.
Means that
The server cannot find it.
So we also have signs about that, and also it means that some of the issues are retriable, some of the issues are not persistent. For example, 410 gone. Anyone heard of that status code? That's the status code that says to us that the content actually went off, and we're gonna see how it affects us in different cases. The most classic one is 400. I guess everyone saw that request. So for example, I'm sending some illegal formatted header or payload or anything else that made the server angry. Not angry as in crashing, not angry might as throw an exception, but angry as I'm not willing to accept your request. And that's the way we may describe to the client that his request was invalid.
401, anyone familiar with 401? 4143? Unauthorized, correct. So is it retriable?
Yes.
By definition, yes. You are supposed to retry with proper credentials. This is what it means. Right. Want to talk a bit about 409 conflict? Anyone knows that one? 409 conflict. No? So obviously no one is using optimistic locking, right? REST, locking, anyone? No, you're not programming or something? I don't know. Okay, so let's suppose that I send a post request to a server. Okay? Yeah, you should be ashamed of yourself.
I am.
Good.
Always.
Okay, cool.
Stay on my back.
Okay, cool. So let's say that you created a resource on the internet using put, or let's say that you're modifying a resource on the internet using a post. Okay? It could be that at the same time, someone else is changing the same resource, right? So, like, how do you know who wins? How do you know that you're not changing it together, or that the version that I have is stale because he modified it, before I could make my modifications? So this is why you have 509 conflict, And this is basically the underpinning of a mechanism known as optimistic locking, where I send the number in the header, I send the version that I have to the server, and he says, okay, the version that you're trying to modify is stale. There was a conflict. Someone else changed it at the same time. Go get the resource again, do whatever you wanted again, okay, and then make the modification. You basically run in a loop until eventually you succeed. Okay, so this is what conflict means. It's actually very, very important. Yes?
Does the browser do the retry by itself, or do the...
So this is mostly not for browsers, okay, unless you have JavaScript code that handles this. Mostly you would find it on servers that work with databases or RESTful services and that kind of stuff.
Maybe like Terraform maybe use it.
Yes, Terraform as well. Request timeout, that one's pretty obvious, right? There was a timeout. You can try again. Hopefully there will not be a timeout in the second request. But request, often you would get it if you're sending the wrong content type, for example. You're asking for XML and the server doesn't know how to serve XML. 451, unavailable for legal reasons. Recently added. Anyone knows why 451? Fahrenheit 451. Anyone read the book? Yeah. So that's why. Okay, it's referencing the book. Kind of a geek joke. Yeah. 402 is my personal favorite. Payment required. Yeah. That's my Jewish side. And 403 forbidden. Yeah, you're not allowed to access this one. You don't have permissions. 404 not found. Very famous one. 401 and 404. I talked about that in a bit. Method not allowed. What's this one?
Method type.
Like a port put for
Put for read-only resource, trace that the server is not willing to accept. You send duck as a method, you might get method not allowed. You get the point. Unsupported media type, again, content negotiation failed. Sado? Achla.
About 418.
Sorry?
418.
For what?
418.
cake.
418, oh yeah. Also, there's another personal favorite. Anyone, I'm not a teapot. Yes. So look it up. In the teapot protocol on the internet, nice RFC. Yeah, it's amazing. There was actually another one, by the way. There's a coffee brewing protocol. Okay, and there's a tea brewing protocol. Yeah, it came a few years after. If anyone wants to build a machine that makes this, go look at the RFC. It's really cool. Yes. Okay. 404 versus 410. Okay, so Michael mentioned this a bit earlier. Okay, 404 means not found, but it may be available later. Okay, maybe at a later time someone would put this page, or if you have a proxy, okay, the proxy may have cached what is known as a negative cache, meaning that it cached that there isn't a page there, and later someone put the page on, or maybe it couldn't connect and it couldn't find a page, or whatever reason. So 404 means I couldn't find it, but it could be available at some point in the future. Okay, and 410 means something different. It means that it's gone. It was there, but someone deleted it, and it's never, ever coming back. Okay, why is this distinction important? Anyone has ideas?
Keep retrying.
Yes, that's actually very good. So, for example, if I want content, if I removed content and I wanted to remove from Google or Yahoo or Bing or whatever search engine is out there. Alta Vista, yes. What? Who is Alta Vista anymore? Yandex. So if you wanted to move from indices, like search indices and places like that, you need to tell the crawler, okay, that this content is gone. It's never going to be there anymore, and they should purge it from all the caches and the indices and stuff like that. So this is why we have 410. Okay, both of them are cacheable by proxies, which is very important to understand. Which is why even if you're giving 404 in your servers, this is something that most people forget. Caching headers for 404. If you don't put caching headers on 404, this might be cached forever. And if you ever put content again on that page, that's going to be a problem. Now, why is this a problem? 404 is something that you might get for dynamic addresses, meaning that if I ask a server for a random address, okay, I'm going to get a response, and it's going to be cached by the CDN, and I can do something known as 404 poisoning. Anyone heard of this? 404 poisoning? No? So basically the idea is that I ask for like a bunch of pages that might at some point be added, and I cause the CDN to cache that those pages are not existing, and then later when someone added those pages and all the users are going through the CDN, and the CDN says, hey, this page doesn't exist. Why? Because it cached it doesn't exist. Okay, so this is known as 404 poisoning. The way to solve this is to make sure that you have the caching headers properly set up even on 404 pages. Now, we showed those slides yesterday to a friend of ours, and he told us a nice story. As it turns out, Terraform providers actually do not handle 410 as they should. And what happened to them is that proxy gave Terraform a 404 response for one of the providers. So Terraform was like, okay, so this resource does not exist. So it recreated it. And that was like, oh shit, yeah. So this is why this nuance is very, very important. Yeah.
So let's talk about server errors, the most fun part in the slides. We have many status codes to describe server errors, but let's should talk about those four guys. 500, internal server error. That generic status code are saying some shit happened. Basically, it means that maybe your data center is on fire, maybe any bad thing happened, maybe again the Jewish rise. Many things can happen, and not always we can distinguish them, so we just return 500. On the other hand, we have 502. Does anyone know what's 502 and 504?
503.
503 is later. Now we're on 502, 504. Anyone? Cool. Anyone use proxy, load balancer, anything? ELB, ALB, some kind of those things. What happened when your ALB, ELB, any wildcard load balancer you're using is not being able to access your backend? What happens?
So you get timeout and it returns 504.
Sorry?
You get a timeout and it returns 504.
So why we have 502 and 504 if it didn't manage to talk with the backend? Why we're separating between those?
The ALB, for example, with the hostname that it doesn't know what to do with the request. So.
Yeah, that's correct. That's correct example. It's one of those things. Maybe our application just returned malformed response because our backend made some mistake and returned malformed bad request. So we want to distinguish between those cases that our backend is not available because of timeouts. So for example, if our backend is smart enough to do back pressure, it's a simple strategy just to delay and push back other clients. So we're going to see 504. And we may see 502 when something bad happens between your app to the proxy itself. Now 503, the most fun thing, service unavailable, which is more related to your example. What happens if I'm trying to access a resource that doesn't have any backends anymore, doesn't allow to be served. So 503 says, hey, I literally can't handle that request at the moment. It's not like I have issues with my backends. It's I literally can't handle your request. So back off, please.
So now we'll go back to the workshop. So go back to your instances, and we're going to do exercise 2. Yes, I know, you're all so excited. Yes, yes, thank you so much. Okay, so level 2. 1 second, and I'm going to put the README here. Mm-hmm. So yes, GitHub. Redirect. So we talked a little bit about redirect before. Okay, this time we're going to implement redirect. So you remember I showed you the send header function before that we used in Python. And you can use that to create a redirect using the location header. Okay, you have all the references here on the page. And you can try some fun things like sending random redirects instead of the same redirect every time. And basically go look how the browser behaves with redirect. So go and hack, and we're going to go through you and help you out if you need to. Yeah.
So, who still haven't solved level 2? Please raise your hands. Everyone solved. That's amazing. So it's gonna save me the live coding time. So basically, so we can see that we want to do a redirect, and we have two things that we need to do. First is to define the status code itself. So I want to set send response, let's say 3.0. מה זה פה? 1 or 2? Yeah, 3 or 1. Redirect. Then we want to add another header called location. Science. No, and those two lines including the handles. And eventually we have the end handles. And those the only two things that we need to do in order to do redirect. Have you tried to do redirect loops? And how your browser behaved?
It looped.
Anyone knows how much loops need to occur before your browser says them and stopping doing that? How much? That's a good guess. I actually don't have the info, so you have an open question.
10.
Someone says me here that it's 10. This guy. And now, before we're going to lunch, I want to show you really nice things that you can do with HTTP. So, who likes security? Ooh, nobody. Have anyone heard of that? Cache poison denial of service. I'm gonna show you one of the most ridiculous things you could imagine that you can do simply with HTTP. An actual attack that's been exploited in many CDNs. So we have a malicious client. This client says or sends a request to a main page, let's say index.html, but he adds some malicious header, something that's gonna cause our application to return 400. Remember 400 bad request? Our application can't serve that. So it seems like a legit request, right? I'm just trying to get the main page. And yet I'm adding some header that's causing the application to be mad. What later happens? Our proxy, CDN cache, decides to cache that response. So think that one client can disturb the index.html cache and stop the whole flow for the rest of the clients. Only single request of a single client causing all the rest of the clients to get also 400, although they're legitimate clients, because one client made a malicious header. There's a nice video showing how this guy stops the site by single request. So he set up a site on top of CloudFront. And then this guy just sending malformed requests to every asset of the page, like you can see in this really small video. This client gonna now send simple request, malicious request that's gonna cause the backend to hate you, to hate the endpoint. And now he's sending the request like legitimate client. You see the logo is not returning anymore. And it was just one request that caused all of the people to experience the site in a bad way. And then he says, okay, I'm gonna continue to the CSS in this case. And now he's gonna attack the CSS file and causing the server return 400 to the CSS. What's gonna happen now when he's gonna refresh? Correct, no CSS. You see how this protocol is so simple, also to abuse. You could easily cause applications to crash and cause your clients bad experience just because one knows how to open his NC and send malformed request and do whatever he wants. Eventually I'm gonna finish this video. It finish up that nobody can access the website. So easy, one person, few HTTP requests. And remember, try not to cache such things. If you're gonna cache 400, think of that. Please think of your different users, and if you're gonna do that, if you're gonna do that, make sure you know how to distinguish between requests, because otherwise you might crash your website to all of your people.
So let's go back. Content negotiation. So if you remember, we said that part of the features of HTTP, it allows you to negotiate on how you want to communicate with your server. So I have a few main headers to do that. For example, who are you, user agent? Your user agent is part of the negotiation, telling us data of who am I. Then we can specify which format, which result we want to get back by using the accept header. So as in the previous example, we sent a request asking for application JSON. We use the accept header to notice or to note to the server that, hey, we want to get back the payload as JSON. Then we can say how we want to encode in what the language, what the char set. We have different headers to create a negotiation with the server. So in this example, we can say, hey, can you send me text HTML response, and can you gzip it, and can you return me it in English because I'm speaking English and I need UTF-8 char set for results. We can tell all those data to the server. Important thing to mention, the server does not have to comply with you. So we have another two nice status codes, 300 and 406, that says part of our operations are not acceptable. So, for example, I'm trying to ask and the accept header to get back application XML because I'm working at IBM or other reasons, obviously. And the server says, no, I can't do that, I'm just supporting JSON. So the negotiation is a recommendation, it's not a must. You may and you can say to the server how you'd like to get a response back, but the server can either reject your request by giving you the correct response headers, or it just can ignore you. Like we saw at the small Google example, that even though we ask for UTF-8, or assumingly ask for UTF-8, we still got ISO back. Let's talk very briefly about cookies. So, as I mentioned, HTTP is stateless protocol. It does not maintain any state between different requests. In order to do so, we have a simple thing called cookies. Cookies is basically another header that the client and the server can pass it on each round trip of request response to provide a state. So for example, the very simple example where I was trying to send a request to the server saying, hey, my name is DOD, DevOpsDays. The server returns a header called setCookie. setCookie says, sure, I took your state and I'm giving it to you back so you could save that state. The client says, Sababa, and then says, okay, I'm sending you a new request, but I'm not saying explicitly what my name. I'm just sending again back the cookie you defined. Using cookies, we can keep track. We can keep sessions. We even can monitor and track people, and that's basically Google in a nutshell. And just the smallest thing, cookies are sent in plain text, so I'm not talking about SSL or cases that the connection is encryption. I'm just talking plainly that the headers are plain text, including the cookies header. So try not to keep sensitive data as a plain text, because people will and might steal it. The common behavior for many servers is to either keep a hashed value on the client, or encrypted value, on the client, or keep session files like a classical PHP that you can create session. It actually stores the state at some /tmp/some path, and the client just have some identifier. Hey, that's my number is 123. Please give me the state that relates to that number. Avishai, any comments?
Nope.
Caching, and please welcome Avishai back to caching.
Thank you very much. Yes, he knows my cache is stale. So anyway, so why are we doing caching? Anyone? Performance, that's one reason.
Save network unnecessary.
Save network bandwidth, that's another reason.
Not online, offline.
Don't read the text, come on. Okay, so all those reasons are correct. So in the early days of the internet, there used to be something called transparent proxies. Your ISP would basically lie to you and say, oh yeah, I'm giving you like, back in the day it was like 28 kilobytes because we had like shitty modems and shit. And they were like, oh, we don't have enough bandwidth going to Europe, so we're going to cache everything without you knowing, of course, because why would they tell you? And therefore, we would save all the network bandwidth, upstream. They'll still do that because just think about this. Netflix, for example. Netflix is a lot of data, especially in HD. So if everyone together would watch, I don't know, Game of Thrones or whatever, it's not on Netflix, but you get the point. If they all watched Game of Thrones together, this would be like gazillion bytes and would clog all the uplinks. By the way, anyone knows how many uplinks we have from Israel? How many? כמה? שניים? כן? Med 1, Basic International. What's the third one?
I'll open the map.
Okay, so we'll get a response to that. I know about 3 ones. I don't remember who the third one is. So not a lot of uplinks actually. It's pretty problematic. In other places that are saner than us and have like ground connection, it's easier. They just put fiber optics in the ground and they have better connections. In Israel, it's kind of an island state, although it's not technically an island, but for various reasons I'm not going to go into. We can't pass land cables and it's shitty, so we have this problem. But around the world, everyone is doing caching. And the second reason is because of latency. Okay, we talked about it when we talked about 5. Really?
2 from Haifa and 3 from Tel Aviv.
Really? So Basic Benlumi, Med 1. Who are the other ones? Okay, I'll get back to us. Fact checker. Good.
So, Jonah.
Okay.
Lev Submarine and Med Methodist, that's from Tel Aviv.
Okay.
And from Haifa, again, Med Methodist, actually connected and Tamarez North.
Okay, nice. Good to know. Cool. So basically, the other reason was latency. If you remember, we talked about it when we talked about the connection initialization phase. But also this relates to how long it takes to bring all the content to you. So it's easier to keep it close to us. And nowadays, the way the internet works is you have what is called POPs, points of presence. Okay, and most of the CDNs and the big vendors like Facebook and Google and Amazon, they have POPs, which is like usually a rack or a few servers that they put in the ISPs, okay, in the data center of the ISPs, and you get your content, whether it's Netflix or YouTube or whatever, you get it from the POP, you don't get it from the data center, and basically what they do is they cache the content locally, okay? But there is another type of caching, which is local cache, your browser, okay? Your browser is, although it's not a proxy, it can also cache, which has a lot of very nice effects. First of all, you don't have to go to the network. You can save the mobile connection or the connection at home, whatever. You don't have to go to the network to fetch resources that you already have. And a lot of the resources that we use, think about images, CSS, stuff like that, they don't change much, okay? So you can cache it for a very, very long time. And in fact, if you cache the HTML itself as well, you can actually work completely offline for a lot of stuff. So think about JavaScript applications, for example. A lot of the JavaScript applications, if they don't need to save state remotely, they can work completely offline once you have all the assets loaded. So cache really helps there, and it's pretty cool. Unfortunately, a lot of web developers are not aware of this, and they start implementing stupid hacks like web workers and use local storage and stuff like that, just to keep the application working offline, although there's really no need. You can just use caching that is properly configured. Okay, so the distinction we have is between private cachers, cachers and shared cachers. Okay, the private cache means that only one user is using that cache. This is your browser, for example, and the shared caches are proxies. Okay, a lot of people use the same proxy. So this proxy has to differentiate between content and know whether it's personalized or not. Otherwise, the attack that Michael showed it would basically have the same effect. I would see content that is supposed to be seen by other people. You'd be amazed how many times this actually happened on the internet, and people saw like pages with other people's names and stuff like that. Pretty horrible. So you're not basically if you're designing an application, make sure that if there's something personalized, you make sure that this is not cached using the headers. And lastly, there's something called forward and reverse proxies. Anyone knows the difference between the forward and reverse proxy?
Yeah, reverse proxy is shielding the servers.
Yes.
And forward is shielding the client.
Exactly. So the forward proxy is when I as a client, I try to connect to a server, and the proxy is on the way, and it receives the request, okay, and says, okay, I'll go to the backend for you, for the client, and I will fetch the content. And reverse proxy is exactly the other way around, okay? It's shielding the server, okay? So I get to the reverse proxy, and the reverse proxy only knows like one or two servers or whatever, and talks to a lot of clients. So it's like basically the same, but in reverse, hence the name reverse proxy. You would find the forward proxies in CDNs mostly and stuff like that, or ISPs, mostly ISPs actually, and the reverse proxies you would usually find in large companies like Wix or Facebook or whatever, or like the Nginx that you have in front of your application is technically a reverse proxy. So that's basically the difference. What does a CDN do?
Basically delivers content and provides you a place to cache your stuff.
Yeah, so CDN does all of this and much more. They provide TCP acceleration, they provide SSL termination, they provide caching, they sometimes provide even workers that allow you to deploy some code. At the edges, they actually do a lot of stuff. They do all of this and more. The most important thing to know about caching is that caching needs to preserve something that is called semantic coherence. Okay, what is semantic coherence? It's a basic and very simple law. You never ever break the behavior of the browser, ever. This is the way it's supposed to work. Caching needs to be transparent, and it should not change the way that the application or the protocol works. Okay, and if it does, it's a bug. Okay, what happens in practice? Come on, you all work on the internet. It's broken. You know it's broken. Okay, so but in theory, this is how it's supposed to work. Cool. So how does caching work? Okay, first of all, every entity that is cached has a key. Okay, usually the key is just the URL, okay, but often it's the method plus the URI. Most of the CDNs and proxies are configured such that they only cache get. Okay, they don't cache post or put for obvious reasons. So it's like this is why often it's only the URI as the cache key. Okay, but what happens when you have a personalized request? Let's think about mobile and desktop requests. So how does the server know that I'm coming from a mobile client?
User headers?
Which header? User agent, that is correct. So content negotiation, remember, you have the user agent header. So this is how the server knows whether if you're using a mobile client or not, and knows to deliver the mobile version of a website. Okay. So how do we make sure that the cache delivers the mobile version to the mobile clients and the desktop version to the desktop clients? If it's cached, and the key is only the URI, what?
In the user agent.
Exactly, we have a subkey. Okay, so this is why we have the var header. The var header basically tells the proxy, okay, you need the subkey, and the subkey should be composed of the following headers. Usually it's user agent, but it can also be any other header that you want. Okay, so you can customize this. Okay, and if your CDN and all of them, of course, support this, then you can basically vary the cache by whichever combination of headers you want. Okay, you don't want to put too many headers there because it's going to be inefficient, but just enough so that there are no problems. You also need to tell whoever's caching how long this version is going to be valid for. Okay, so basically we have 3 states for cache. We have fresh, stale, and expired. Okay, fresh means it's new. I need to get a new copy. Okay, what is the difference between stale and expired? Anyone want to take a guess?
Stale, it still exists, but nobody uses it. Maybe it's not usable.
Okay, so the difference is this. Stales mean that yes, there is a new version. I should probably get it, But as long as I didn't get it, I can still give you that old content and you can use it. Okay? Whereas expired means I can't use this anymore. Okay? Whether or not I can talk to the server, I can't use it. So for example, if you're talking about the browser, it can, if it's offline, okay, you don't have a connection, you can still use a stale version, whereas expired means that you can't use it. Okay, so if you're online, it's not going to work if you're offline. So this is the difference between stale and expired. How do we know if it's stale or expired or whatever? This is where the headers come in. We have the expires header and the cache control header. Okay, so the cache control header is a header that has a lot of directives that tells the cache how to behave. Okay, one of them is max age, which means like how long we can cache it for before it becomes stale, and then we have the expires header, which basically tells the cacher how long before this page becomes expired and we can't use it anymore. If we want to disable caching, okay, the easiest way is just give expired with a negative number, like -1, and this means that this is already expired and will always be expired, so don't cache it. There's also, if you look at the cache control in documentation, later you can do that, you'll see that there's like no store, no cache, and all kinds of directives that tell the cacher how to behave and when not to cache stuff, and so on and so on and so on. So what is write-through? Anyone knows? Write-through? Yes, you in the back?
You just use it like as a write-through. I don't know how to otherwise describe it.
Okay, so let's say that we have a method that is supposed to write something to the server. Okay, let's say post. Okay, you can actually cache post requests. It's allowed. Like most CDNs don't do this, but you can cache post requests. However, because post requests are supposed to have a side effect, this is where something called write-through, okay, comes in. Write-through means that although the content that is returned, the body that is returned might be cached, the proxy still has to talk to the server. Okay, it has to tell it, okay, there was a post request, and here are the parameters of that post request. Why? To preserve semantic coherence. Okay, maybe the server needs to trigger some side effect, like something in the database, or maybe it's used for tracking or whatever. For whatever reason, okay, the server still has to accept the request, but the body can come back from the CDN or from the proxy, which does sometimes save a lot of bandwidth. Okay, so think about really large content. Okay, so it does that.
But it validates the request before you can see the value.
So this is like it's not an edge case, but it's a nuanced case. So sometimes, okay, what happens is it returns a response to you, and then asynchronously in the background talks to the server. And this can happen for a number of reasons. Let's say that you have a stale request, but the cache is stale. I can still serve you the content and get a fresh version so that next time someone asks for this content, it's always fresh, okay? Also, there's something like, you remember we talked about the head request? Did anyone wonder what the head request is used for? What do you think can be done with a head request?
You can see if a resource is existing.
Oh, first of all, yes, I can see if it's existing. What else can I do with it?
To update, to see if the cache needs to be...
Exactly, to see if the cache needs updating. So I can periodically ask the server, hi, I've got this resource that I cached like 2 days ago, give me the metadata so I can see if there's a new version, okay? So there are a few headers that, we haven't talked about them yet, that give you basically, sorry, it's not this one. A few headers that tell you like the age of the page. You remember we had, we saw like dates, okay, when the content was created. So I can go and I can check if there's a newer version that was generated later, and then asynchronously I can get the new version and mirror it, so to speak, and I can do that. I can periodically check for it very cheaply using the head method. Okay, so this is why it exists. So another very nice thing is something called conditional request. I can ask the server and I can tell it, listen, this is the version I have. Okay, so bring me back the body, but only if you have a newer body. Otherwise, I already have a version and it's fine, so I don't need you to give me like 10 megabytes if I don't need it, if the version that I have is valid. So how is this done? There are two very important headers. First header is etag, okay, which is basically a hash, usually MD5. It's a hash that identifies the content, Okay. If you remember, hash is a function that basically changes if anything in the content in the content that is hashed is changing. Okay, so one bit that is changing the content will trigger a change in the hash. It's no longer going to be the same hash. So if I tell the server what is the hash of the content I have, it can tell me, okay, yes, you have the current version. There's no need for me to return more data to you. And same happens with last modified. I can do the same with date. I can tell you, this is the version I have. It's from, I don't know, 2 days ago. And then the server says, okay, this was not modified in the time since that you've seen this last. So there's no reason for me to give you new content. So there are two headers involved. The request header is if modified since. Okay, I asked you, has this resource been modified since I last saw it? And the server can respond with, like in the initial response, tell you this was last modified in this date. When was this content generated? And if there's no need to return anything, the server will return 304, which is not modified. Okay, and if it was modified and you need to get a body back, it will respond with 200 OK and give you the body of the new version. Now, there are two types of validation, strong and weak validation. The difference is that strong validation means bit per bit validation, meaning it's exactly the same content bit per bit. And weak validation means it's equivalent. It's not exactly the same, but it is equivalent. Okay, maybe unimportant stuff has changed, like the date signature. A lot of pages are dynamic. They might have a date signature of when this page was generated. It's like one string. It doesn't change anything that the user cares about, but still the checksum would be different. Okay, so in cases like that, we want to use weak validation. Okay, so look it up. It's pretty cool. It's being used on the internet in variety of situations. So the etag header is kind of nice. It's used for a lot of stuff, not only caching. Basically, one of the users, the most common users, especially in backends, if you remember, we talked a little bit about optimistic locking. So how do we know if a resource has changed? If a resource was changed, the etag, the checks of the resource will also change. So when we do, if you remember the 409 response, okay, when we say we do a put or a post to a server and say we want to change this entity, and we give it the etag of the resource that we read in the previous GET request, okay, and if the etag does not match the new checksum of the resource, then we get 409. Okay, this is what we get. Another very common use case is to resume partial downloads. So what is a partial download? Let's say that I want to download a video from S3, and I downloaded 300 megabytes, and then 1 megabyte was corrupted. Okay? What do? Do I have to start downloading the entire file again? No, that would be done. So there's something called byte range request. I can ask for just a part of the file. I can say to the server, give me from megabyte, from this range, the start of the range, I give it like the byte sequence of where it starts until this part, like 100 megabytes from here to here, okay? And I use the etag to validate that indeed I got the entire file, okay? Because remember, if the checksum is the same, this means that I now have the full payload. So I can validate that I got everything. Is that clear? Yeah, cool. Awesome.
Never saw it
used?
Yeah.
You actually have. So you remember FlashCat? Excel, FlashCat, all the multi-downloaders stuff. So actually a lot of downloaders use this. They just don't tell you, just don't tell you that they do this. Everything that updates in the background, they usually do it for optimization reasons. It's also being used for videos. For example, if you watch a video file, so originally the video implementation for iPhone and actually the HTML5 video thingy also works with byte range. Okay, kind of. So it's actually been used, but you don't actually know this. There is one very shady use case for etag, which is tracking users. Okay, so like the way people use cookies, you can actually use etag to track people. If I give you an image or some asset that I can embed in a web page, then the browser will hit that asset every time that you load the page. And if the server gives you an E tag, what are you going to do? You're going to issue a conditional request with the same E tag, right? But an E tag doesn't have to be an MD5. It can be just a UID or some random generated string, which can be used to identify the user, okay? So this is how some, I won't call them malicious, but ill-behaving parties on the internet, they use this tactic to track users. It's considered very bad practice. You might get sued if you do this. If you remember, a lot of regulations force you today to inform the user that you're using cookies to track, or even not to track, but you're using cookies. So basically, if you use this kind of method to track users, you can't inform the user that you're doing that. And of course, there's no consent. So depends how shady you want to be. I don't know, your problem. You didn't hear it from me. I don't want to get sued.
Cool. So I actually want to talk about last thing before we're going to get back to levels. Virtual hosting. I mentioned this term, I think, a few times before, and I haven't actually explained what's that. So let's say we want to develop a server, but we're a cheap company, and we can only have one EC2 instance because, again, we're a cheap company. And yet we have many clients, many big famous clients like very big client.com, and they want to have their own website on our server, and we need somehow to distinguish between them. So using the host header, we can redirect the same request on the server differently to different pages. And on this thing, I want to tell you a true, funny, or not funny, more like security story. Have any one of you heard about a company called Signal? Raise your hands. Only one. Shane. So they're a company that basically does text messaging, but they also have their own encryption protocol, and they did an amazing job like keeping you anonymous. Or I'm still doing this anonymous because nothing is anonymous actually. But they were banned in Egypt, if I remember correctly, and they tried to bypass it. So how did they bypass it? There's a few ways to block traffic on the ISP level. They can block your DNS queries. So if they're trying to resolve signal server.signal.com, they may block the resolvement. They may block the IP addresses of their load balancers. And basically, I think that's the two main methods that they can firewall and block you out from your service. So one day they did new client release and they changed the domain to be Amazon or subdomain of Amazon.com. How the fuck that works, right? Like, why you're trying to communicate with Amazon? So they just went to CloudFront, added a new account on CloudFront. They sat behind CloudFront and changed the client to use one of the domains that CloudFront is serving. But after the DNS resolvement happened, first of all, you can't block some of Amazon domains because nobody gonna do that in a big country. Second of all, the resolved IP is the CDN in this case. And then after the handshake happened and after the SSL handshake happened, they sent a different host header saying, no, actually go to signal.com. So they use different domain, upfront of a CDN, to internally just modify the host header and say, no, actually I'm other domain. It's easy manipulation you could do with these headers. And saying that, I want us to get back to our hands-on workshop. Some of you already managed to finish level 4. Raise your hands.
No one?
Amazing. So level 4 is going to talk about caching, and level 5 is going to talk about virtual hosting. So let's going to get back to our keyboard and start coding.
Okay, so if any of you had problems with the caching thingy, yeah, of course. Okay, so here's what's going on. Are you using Chrome or Firefox, right? Okay, cool. So what's happening is if you look at the console, okay, and you look at the request that Firefox is sending, it's sending what is called as a conditional request. Okay, it's sending the if modified since thingy. Remember we talked about it? Open the network console of the Firefox or Chrome and you'll see it. And the problem is that your server does not implement the second part of the caching protocol, which is, if you remember, you're supposed to look at the if modified since. And what do you return if it wasn't modified? 3 or 4. Yes, this is why. Okay, so that's the reason why it doesn't work. You can either implement 3 or 4 now if you want, or just move on and then we'll fix it later. There's a way to tell the server not to send conditional requests to allow for offline operation, but too complicated now, so forget about it. Sorry about that.
But it's sending 200.
What, sorry?
It is sending 200.
Yes, the first request is supposed to be responded by 200. Second request, when the server sees that you already have a version that is not stale, you're supposed to return 3 or 4 not modified.
It's not doing that.
Yes, our server does not implement this. This is why. This is like our server that is supposed to do that.
Who is on level 5 now? So those who are stuck on level 4 because of the caching issues, you just can continue to level 5 and afterwards we'll update it.
Yes, but first of all, let's do a small break here and we'll go through level 3, which we haven't gone through yet. Then we'll talk about it for a bit. And then we'll go through level 4 and explain it, and we'll do the rest. Okay, so level 3. So level 3 was just supposed to be doing, you need to send, of course, properly formatted body, of course, and the headers. So the first header that we need to send is send header. Okay. So first thing we need to do is we need to send a response. Okay, send response 200, okay. And second thing is we need to send a header. Which header are we supposed to send? Content. Length, yes, type and length. So type would be text HTML in this case. So, and self send header, content, length. And the length is of course just the length of the body, so it's pretty easy. Okay, and and then we need to write the body. But remember, so we also need to terminate the headers first. So send header. And headers. Oof. By the way, fun fact, go to GitHub and in the search part of GitHub, just type in semicolon, like columns, and then WQ, and see the results that you get. Just very amusing. Just try it. Okay, so end headers, and now we need to send the body. So we just do W file, write the body, and we flush it. Okay, and that's pretty much it. Now, has anyone tried sending a body, like a content length which is wrong, smaller or larger or smaller than, okay, what happened?
In Firefox it worked just fine, in curl it either cut off before the end or told you how many characters were missing.
Exactly, because what happens is that usually the client would just read as many bytes as it sees on the content length, and if there are not enough bytes, meaning that the content length is smaller, then you would see the body cut off. And if it's too long, it might be stuck until timeout, of course, and then to just flush it to the screen, but it might cause other problems. So that's the idea, basically. Has anyone implemented gzip? No? Okay. So as an exercise, you might want to do that later. It's pretty easy and it's very nice. So just a small question. Suppose you're sending a body, okay? And let's say that the body is very, very long. Let's say 100 megabytes. What would you do? So chunks, that's one option, okay? And another option is to just buffer it and then send it in parts. Just flush it to the TCP stream in a loop. Sort of, not necessarily chunked response. You do know in advance what's the size of the content, so you just loop it on like here with the write. You can just write it in chunks, but the transfer encoding doesn't need to change. It's still like the normal transfer encoding. So that's also one way. And we're going to do that thing. Cool. Any questions about this? Cool. another question. So you see that the encoding here is UTF-8, right? So anyone tried the emoji thingy? Okay, what happened?
I got this weird arcade symbol.
Yeah.
With like ein umlaut.
Yes. So why does that happen?
Because of the encoding.
Because of the encoding. Okay. So Unicode basically, when you use emoji, Unicode, like the bottom part of Unicode, is identical to ASCII. Okay, all the the normal characters would work because it's the same encoding. Basically, Unicode is a superset of ASCII, but Hebrew and like Chinese and all those weird languages and emojis and all that stuff, they are different. Okay, in Unicode they exist. They might not exist in ASCII or any of the other ISO encodings. So you would get really weird results. And that's why it doesn't work. Anyone remembers the old days before we had standardized internet and we had like really weird encodings for Hebrew? Yeah? Anyone? Remember? Okay, cool. Okay. So back in the day, we actually had to manually select encoding for web pages. It was incredibly annoying and like no one wants to go back to this. So thank God we now have properly set content type. So great, yay for us. Cool. Okay, level 4. So we do apologize for the problem with the not modified thingy. This is like the basic solution of level 4. I'll just go for it. Okay. So as before, we have char set and the content type, content length, and all of that. Now we see cache control. Okay, so I've put only one directive of cache control. There are quite a few you can read in the documentation, and then I've set the expire to some, sometime in the distant future, about a year from now. And then I sent a weak ETAG. Okay, the W/ means it's weak validation. Okay, and I didn't bother to actually compute the MD5, but like it's not a problem with Python. Just import MD5 if you want. And then I put last modified and the date of a few days ago, because why not? And that's basically everything you need. Like expires and cache control, that's basically everything you need. And the reason why, for most of you, it didn't work is that if you look at the browser console, the first request is 200, will get 200 OK. The browser will get a response. It will see that it has last modified and ETAG headers. And then on the second request, it will send if modified since, okay? And of course the ETAG is in, if you remember the other header, do you remember the header? No? If modified since, and what was the other one?
Modified.
Sorry?
No, if not modified.
If modified since, and there was another one with the ETAG? Not expired, no.
If not match?
Sorry? If not match. Very nice. Very good. So, it will send if match or if not matched, and if modified or if not modified. And our server will basically need to see that the second request, like here we would have to have like if path, we would have to have if self headers and find of course a header which is like if modified since, and parse it and like actually do the calculation and return 304. Okay, and then the browser knows, okay, there's not going to be any content because I already have it and it will display what it displayed before. There is a way to craft the header such that the browser will not even send 304. Okay, I'm not going to go into that now. We'll fix it for next time we do this workshop, so I do apologize for this. Yeah. Questions about level 4? Yes.
Is there any advantage of time-based calculation instead of hashes?
Oh, that's an excellent question, actually. So, technically speaking, ETAG does not have to be a hash. So, like, you can just make up whatever UID you want. It's just easier that hash, and for downloads, it helps because you actually want to compute the hash. And technically speaking, it's probably better and more correct to use ETAG than dates. But often you don't actually care about the content. You care about dates. So it really depends on the application. Think about, for example, stock, like if you have some interface that gives you information about stocks, okay, so that might be relevant for like 15 minutes. Why? Because of the business reasons. After 15 minutes, you want to refresh because the stock prices went up or down or whatever. Maybe it's results from I don't know, horse races. Okay, so from the application perspective, you actually care about time. So this is why it's mostly an applicative issue if you want to use ETAG or time.
Also, hashing costs CPU cycles, so it's easier to save metadata when the document was last modified rather than computing every time MD5 sum. Obviously, you can put it aside, but if you're gonna do this calculation every time, you're just gonna waste CPU cycles.
So cool. Excellent. So let's go and talk about level 5 for a second. So virtual hosting, okay? So Michael mentioned this before. The idea with virtual hosting is that we look at the host header, and based on the host header, we decide what to do. In real servers, you might have multiple, not applications, but servers hosted on the same installation. Think about WordPress.org, okay? There are many WordPress sites hosted on WordPress.org, and you need to look at the host header to decide which site to actually serve. So what we do is we look at the header, okay? In this case, if you look at the documentation of the Python server, you can see how you access the request headers. It's basically self.headers. And what you need to do is decide and implement the is-domain allowed and get-domain content, and basically decide what to return based on the host header. So that's basically it. Go and hack. Just want to show you something. Okay, so in Firefox and in Chrome, there's something called offline mode, which is, yeah. So if you click offline mode in Chrome or Firefox, and you did the exercise 4, so you can actually see that I'm refreshing, and I still see the same thing. And this works offline perfectly. And if you see at the network console, it tells me that this has been cached. Okay, transfer that's cached. So this is actually how you can verify that you did level 4 properly, despite not implementing the 3 or 4 response. Okay, but we do apologize for this.
Let's see the solution for level 5 and continue to the slides. So the purpose of this task was to see how we can read the host header and how we can easily manipulate. And in these two methods, all we had to do is to implement those both functions. So is-domain allowed is basically reading the host header. What I'm doing here, just reading from the headers array, headers dictionary, the host header. And you see the extra split I'm doing here? If you noticed, the host header contains also the port. So if you're using a custom port, let's say 8080, we would see localhost _ 8080. And since I'm just a nice person, I'm getting rid of this to remove my noise. And then all I do is to check if the domain is inside the dictionary or not. If it's not, we return 400 BET request. You know why we return 400 BET request? And why not something else? The simple answer is the RFC. The RFC says that if you don't get the host header, for example, someone says you malicious headers and does not specify the header, you must return him 400. Let's say someone tried to send a domain that is not as part of our allowed domains. Also, the RFC specifies you should return 400. The reason the RFC tries to specify that, so we would be compatible between our clients. So imagine you'd use one status code to identify that, and others would use different one. Our clients wouldn't know how to behave according to the issue. So the solution for that is to read the header, the host header, check in this very static case whether it's part of our allowed domains or not, and if not, just flash back 400. Any questions for that? Looks simple, straightforward, right? I didn't write here too much complex code, basic string manipulation, nothing complex. How have you tried to check whether this thing works or not? Have anyone managed to go to their browser and write domain1.com and see if it works? Only one? Nice. Can you share us how you did that? Exactly. Every Unix-like operation thingy has a file called etc host. etc host is...
Windows says it as well.
We don't talk about Windows in this room. If you use Windows, no, just kidding. But this file easily can map us domains to static IPs, so we wouldn't actually go and resolve the DNS. What's the second option to check whether our code works or not?
It's localhost to the...
What?
I've added localhost to the...
Yes, also works.
Yes, that also works. And the simplest... Yes.
COS can change the offset.
Thank you. And the most simple way to check whether our code works or not is to send curl with -h. -h host double נקודתיים, double colons, any domain you want. Basically, on the same method, we could send any header we want and check whether we receive them or not. Or Postman, I prefer curl personally, but some people here says Postman.
I said some people use Postman. I didn't say.
He says some people use Postman. I'll be correct. So I want to emphasize curl. Like it's not clear or obvious, but curl is like the most easiest tool to debug 95% of our HTTP issues. The two flags you need to know besides -h is first one, -v. -verbose. It sounds funny, right? But with -verbose, you can see what headers we're sending and what we're getting back. You can easily verify that your payload back is correct or not. And I said two, so I actually want to say -h, but I already said that. So we're just gonna keep with -h and -v. Avishai.
Yes, if you're a civilized person, not like this person here, you don't want to use curl, you want to use a very cool tool called HTTPy, which is something like this, and then boom, it's very nice. It gives you formatted payload, like header stuff, much easier to use than CORL. Just look it up, really cool tool, very nice. Makes your life much easier.
And again, it's written in OGS, so I'm not sure I want to use
Python. Like civilized people.
Yeah, so let's go back to the slides and finish those up and continue with the hands-on part.
Fine.
Connection reuse, the most fun part in our session. So you heard about keepalive, right? We want to make sure our connection may be reusable for other requests. The easiest example I can give, let's assume you open your browser and go into some web server. Let's assume it's your localhost web server. If you open the DevTools, you can see that besides the initial request you sent, it says another request like favicon. And in real sites, usually we also down assets if you're not sitting in CDN or other endpoints. So if we have 5-6 requests gonna happen in a period of few seconds or within a period of a minute, we can reuse the same TCP connection and not doing the round trips that Avishai talked before about them. To do that, we have a connection header that can says, hey, keep alive the connection. This header says to the server, please do not close the connection because there's chance I'm gonna reuse it. If the server is fine and good, it's gonna say, okay, sure, you have X amount of time until the connection gonna get closed. In that time frame, you can send new transactions, new requests, or those requests gonna reuse the same connection. We show here example how you can define timeouts. By the way, fun fact, when I say keep alive, I'm talking about the connection header. Connection header says that you need to keep alive the connection. There's another header called keep alive, which is not saying that you need to keep the connection open. It just gives the attributes on how to keep the connection open. So if you don't say connection keep alive, the keep alive header is meaningless. Fun fact. So the trade-offs of these things is it's basically managing a state. think of your real-world servers. It means that they need to handle the transaction, they need to keep somewhere the connection open, they need to somehow make sure the connection is not idle anymore, because if I'm just sending one request and I'm not going to go back to you, why should I keep that connection open? It's just wasting resources on the machine. And as we said, connections may be stale, because in real world, nothing like TCP is not for fact can work. If I have a connection that just cut off his internet line and we didn't have the fin, it doesn't mean the connection on the server actually going to get close. So the connection might be in time wait or in a state that it's just going to be open. It's just going to keep your file descriptor or a file that's going to keep your resources. And if you're using a threadful server, a fixed size threadful server, you may finish your slots to accept new connections. So managing connection is not easy. It's really not easy. And you're going to see later in the workshop how the fine-tunings of timeouts and idle connections handling can improve that. But without keepalive, I think most of our web application would suck, because we have so much repeating transaction over basic web servers, and the fact that we know and we can keep the same connection to reuse is a nice performance addition.
Yeah. Just something that's nice to try at home. Open, your favorite web page. Might it be Facebook, Twitter, whatever you want. It doesn't matter. And just go to the web console. Hit there's a checkbox you can mark for disable cache, and see how many requests you need to do to get one page. Just count them. Very interesting experiment.
And also, if you do curl-v, you can see if the connection is being reused or not. And our last theme for today is HTTP pipelining. We mentioned that briefly at the beginning. Thank you, service עד הבית, מה שנקרא. Cheers. So basically, as I mentioned, each transaction in HTTP is request response, meaning that once we open a TCP connection and we send in a request, we're waiting for the response to come. What happens if we have 10 requests we need to do concurrently? Should we wait for each request? Shouldn't we? So HTTP 1.1 and later on in HTTP 2, which we won't talk about it, they implemented a concept called pipelining or multiplexing. Basically, as you can see, without pipelining, we're doing a few round trips. We're going to the server, getting the response back to open a new connection or a new transaction, go back and do it sequentially. What if I say we could do batch or multiple requests at the same time to the server? And the guarantees of HTTP 1.1 pipelining is that the responses going to get back on the same order you send the request. So you can, within a single transaction, send a few requests and get them sequentially back, which is nice because you have direct mapping one-to-one of your sequence of sending the request to the payload back. So you don't need to get messy with how do you match one request to the response. HTTP 2 improved it even more with multiplexing. I don't think we're going to have enough time to talk about that, but just a thing that I really suggest for you to search later. What is the problem with HTTP pipelines? Especially search for something called head of blocking line. Head of line blocking. You will surprise that it's not really easy to do that, and sometimes there's interesting issues, and HTTP 3 even solved it even better, but that's even major topic to talk about it.
Streaming in recent years has become very important for various reasons. First of all, everybody wants to do chat and stuff like that, and get real-time feeds of data from the internet, which is really cool. But the question arises, how do we do streaming? You remember that HTTP is a request response-oriented protocol, so you get data, and then you ask for more data, and so on, so on, so on, and it's not really a stream, okay? So how do we get a stream from a request response protocol? So there are a few ways. Originally, they hacked it. Okay, so long polling was one of the original mechanisms that people used to simulate streaming on top of HTTP. And the way long polling works is basically a loop. You issue a request, and instead of responding immediately, the server just holds the connection open, Okay, it doesn't respond to the client. Your client is basically stuck, more or less. And when there's something to send to the client, then it will terminate the connection and return the response. Okay, like flush the response back to you. For example, if there's chat, okay, I would poll the server. I would ask him, is there like new text, new messages for me? And the server would not respond. It will wait. And if during that time you got messages for me, then it would send the messages immediately to me. I would see the messages, render them in the browser, and immediately I would open another polling request to the server. And this goes on in a loop. So usually that loop is like 20 seconds, 60 seconds, whatever, that the connection is held open. And when it terminates, either with data or without data, I just poll again and again and again. This is called long polling. It's a hack. It works fairly well. And it works so well that even SQS and other services online use it. It's basically the fallback of every chat system that I know of. XMPP and stuff like that use it all the time. But there are actually better mechanisms that were added to the HTTP spec later. For example, everyone knows WebSocket, right? Everyone uses WebSocket. What's the problem with WebSocket? One, not all proxies support it. And B, it's fairly complicated. Okay, so there is another mechanism that was introduced for compatibility, and also it's much easier to implement, which is SSC. SSC is more limited than WebSocket. It only allows to stream from the server to the client, whereas WebSocket is a two-way streaming protocol. You can stream from the client to the browser and to the server and vice versa. And SSC is only one way, but it is much simpler than WebSocket. It doesn't require as much state, and also it's compatible with existing proxies, so it works everywhere, even if the proxy doesn't support WebSocket. In this workshop, we actually have an exercise 10, where you can actually implement SSC yourself. It's not hard to do. You can do it in a Python or PHP server in about 6-7 lines, SSC, whereas WebSocket, if you try to implement it, it's like hundreds of lines. So much easier. You would be surprised that a lot of people use WebSocket because they just don't know SSC exists. In many use cases, it's enough to have one-way streaming. You don't need the other side, or like you can implement the other side using long polling or just normal HTTP requests. So there's that. Just look it up. It's very nice. So one more thing. Due to time constraints, it's already 4 o'clock, and we're going to release you so you can go have a drink. If you want, we're going to be here. We're going to help whoever wants to do the more advanced exercises. Next up is level 6, where we go low level, and we start implementing the HTTP server on top of sockets. So if you're interested in low level details, you're welcome to stay. Otherwise, we're going to release you in a second to go have a beer. Okay? Before we say thank you and goodbye, we want to say 2 things. In the GitHub repository, you'll find issues. You know it's there, you've seen it, you know how to use it. Feel free to open issues, also pull requests. We are accepting pull requests. And most important, you know what's most important in GitHub? Stars, yes, please star us. Give us lots of stars. We are not going to abuse them. Of course, we are going to abuse them, but please give them to us anyway. Thank you very much.